All right. Welcome everyone to lecture 16 of Vector 101. Today we're going to continue our discussion of affine geometry. And I will make a couple remarks right at the start. One is that I'm in a different setup than usual today, so if my internet cuts out, I apologize. Hopefully it won't. And then two, this is my second lecture of the week, I guess. If I gave a talk earlier this week on C-frames. And so this lecture had to come together pretty quickly. Um, hopefully it'll go fine. All right. So the first thing we're going to do is actually look at C-frames before we get into affine subspaces, and then we'll talk about different types of linear combinations, an affine combination being one of them. And then we'll talk about how to construct an affine subspace. And so we won't really, I don't think we're going to say too many new things today, but we're certainly going to look at more pictures today, and hopefully that'll clarify some things from Monday. And then also notably, we're not going to be writing any code today. I thought for a while about like what code we could write that would reinforce what we're learning about affine subspaces, and kind of drew a blank. But I'll talk more about that. Yeah, so today's kind of just a picture day. Okay, and then reminders as always, doing the exercises is important. I apologize, the exercises have not been posted for the past 2 weeks. I have them, they're just not posted, so I'll try to do that. And then office hours, as always, are on Saturday at 1 p.m. Pacific. Okay, so when I announced this course, I made a promise. And the promise was you will be guaranteed a 10x improvement in your C-framing or your money back. And of course, that's a joke because this is a free course. If you're watching the recordings and you didn't know that, but I still intend to deliver on this promise. But to deliver on this promise, I need your help, which is I need you to forget everything you know about C-frames. And in this way, if you forget everything, and then I teach you the slightest thing about C-frames, you will have 10x your C-frame knowledge, or 100x or infinity x your C-frame knowledge. So I need you. Yeah. I also think it's funny that in this image, he's throwing out a box of math papers. Okay. Right. So then our motivation for affine subspaces is C-frames. So C-frames are a type of function called an affine transformation. And really, like this is what we want to get to. Affine transformations are cool. But to talk about affine transformations, we first have to talk about affine spaces. And so that's what we're doing this week, and then next week we'll be able to get to the cool stuff. So because you have just forgotten everything about C-frames, I now have to teach you something about C-frames. So I'm going to switch over to my C-frame talk from Tuesday, and we're just going to look at some cool C-frame things, and then we're going to be sufficiently motivated to learn about affine spaces. Okay. All right, so what are some cool things that we can do with C-frames? Well, the most boring thing we can do with C-frame is that we can use it to position a part. So here as a part, and using C-frames, I can translate it, and I can rotate it. But what else can we do? Well, here is this orbiting fire particle effect. Maybe this is some effect in like a magic game, or maybe you could think of these as like pets orbiting your character. So this is sort of C-frames working in tandem with trigonometry here. We could also have a C-frame that rotates around a pivot point that's not the center. So you'll notice instead of the part rotating around its center, it's rotating around this line. And this is actually kind of a bit tricky to do. So the question is in the chat, do they use quaternions for the rotation? No, I'm just using good old-fashioned C-frames here. You can pretty much do the same thing with C-frames as you can with quaternions. Is that strictly true? Probably. Okay, here's another cool thing we can do with C-frames. So often in games, you'll want to inspect a part. So here I can drag it around in front of my screen, and then we can give it a good look. Okay, so hopefully now I have already 10 extra C-frame knowledge. So now we will get back into affine spaces. Okay. So on Monday, we talked about sort of one way to motivate affine spaces, and I'm going to introduce you to another one today. They're very similar. So in R2, we have one distinguished point, like one point that's more special than all of the rest. Can anybody tell me what this point is? And I'll give you a hint that it's on your screen. Exactly right, yeah. So the one special point in R2, in R2 is 0. And so 0 acts as like our reference frame for all other points. So if I have some vector here, well, like I've measured the vector from the origin. And so this is our point of view. But why should this point of view be preferred to all others? It's kind of an arbitrary decision. So then with affine geometry, we remove this arbitrary decision. And we say that like all points of view are equally as valid. So for example, here at this point, this is going to be me. So I'm going to be standing here and I'm going to look in that direction. And the right side of my head is going to be in that direction. And then let's say you are standing right here and you're looking that way. And the right side of your head is in that direction. And we're both looking at, let's see, we're both looking at this point here. So from my point of view, I see this point as having these coordinates. So I'm going to measure along my local x-axis there and along my local y-axis going here. And so I would look at this point and go, all right, well, that's roughly at maybe 2, 2. And then you would look at this point and then you would measure it differently. So in your perspective, you would measure it on the x-axis going the other, going negative, and then along the y-axis there. So maybe in your perspective, that point is roughly maybe like -1, 2. Let's go with that. So we're looking at the same point. We are like describing the same point, but from different points of view. And like the whole point is that's fine. Like no point of view is more correct than another point of view. And so what this means is that like we're no longer stuck to the origin. Like we can just forget about the origin and talk about sort of like linear subspaces, but that no longer go through the origin. And so this gives us an affine subspace. So geometrically, an affine subspace is a linear subspace that can be shifted away from the origin. And I have a couple examples here. All right, are there any questions so far? Okay. As an aside, just kind of to clear up some potential confusion. So like usually in algebra class, you would write y equals mx plus b, and you would call that a line. Really, we should have been calling that an affine line. Like when we mean a linear subspace that is a line that always goes through the origin, whereas like these y equals mx plus b things, these are affine lines, so they don't have to go through the origin. Okay. So what we know is that an affine space is like a linear space that's shifted away from the origin. Now let's talk about what lives in these spaces. So in maybe week 1, I claimed to you that a vector is just an arrow. And this is true. But in an affine space, we now gain another geometric object, which is a point. Oh, this is a good question. So can an affine space still go through the origin? Yeah, it totally can. So linear subspaces are a subset of affine subspaces. So every linear subspace is an affine subspace, but not every affine subspace is a linear subspace, if that makes sense. Okay, cool. Right, we want to talk about what lives in an affine space. How do I want to say this? Okay, we're going to imagine that this slide here, this entire plane, this is some affine subspace. So in this affine subspace, I'm going to put a point here, and I'm going to put a point here. Okay, and we're, all right. And then from these 2 points, I'm going to draw arrows. And I'll draw, let's see, put one there. Okay, so this is going to be, sorry, this vector is going to be v, this vector is going to be w. Now, from my perspective, if I wanted to, okay, I need to, sorry, something isn't adding up about this diagram. Okay, I figured it out. Okay, we're going to be in 3D space here. This is going to be the origin, and I'm going to put some affine subspace just sitting there in space. So there's a plane sitting in space, and I'm going to have 2 points on this plane. So this one will be v, and this one will be w. Now, in a linear subspace, what we can do is like we're allowed to just add v and w, and we know that we're going to end up with another vector that's also in the subspace. But with affine subspaces, this isn't the case. So if I were to take W and add it to V, so something like this, and like the perspective is hard to get right here. So this vector is going to be V plus W. What you're supposed to be seeing, and maybe is like hard to see with my drawing, is that V plus W no longer lives in the affine subspace. Meaning in general, there's no notion of adding points in an affine subspace because you might end up with something that's outside of your subspace. But what we can do is we can subtract points. So similar setup here, I'm going to make this one V. I'll make this one W. And now when we subtract V from W, we get a vector. We get a vector like this. So this is going to be W minus V. Is there any way to add two vectors and get a vector back in the affine subspace, in the affine space? Certainly this is true if your affine subspace is in particular a linear subspace, because we know that in linear subspaces you can add vectors. But in general, I don't think so. No. Okay. So we see that when we add vectors, sometimes we land outside of the affine subspace. But when we subtract a vector, this works out completely fine. And so what we call this W minus V, we call this a displacement vector. So displacement vectors are totally allowed in affine spaces. So then like the inhabitants of this space are two things. So every affine space has points and displacement vectors. So right, I'm running out of space. Here's my affine space again. So we have points and displacement vectors, meaning, so these are points in our affine space and they live in our affine space. And then displacement vectors are like at every point, we can sort of walk in any direction. And these directions are, well, yeah, displacement vectors. Okay, I guess we'll keep going. So we've seen a bit about like, what does an affine space look like? Well, it looks like a linear subspace that can potentially be shifted away from the origin. Now how do we construct an affine subspace? And we've seen two methods to do this. So the first method that we saw on Monday was taking what we call the affine hull of a set of points. So the first method is an affine hull. So on Monday we saw that like if we have 2 points, their affine hull is going to be the line between them. And in particular, this is the set of points. So it's going to be all sums of x1 and x2. So all sums of x1 for all linear combinations of x1 and x2 such that the weights sum to 1. All right, and then the second method that we saw to construct an affine subspace was to encode it as a linear system. And I think I'm going to touch on that later, but for now I want to focus on this affine hull construction. Yeah, sorry. Thanks for clarifying, Aiden. So like, yeah, maybe this wasn't correct. So like the points are the things that live in the subspace, but the displacement vectors are the directions that we're allowed to walk in. Okay. So maybe I got a little bit ambitious and I wanted to show you what an affine hull looks like, but then I thought, why not show you other types of hulls? So I guess we'll go through that now. So the combination that we know the best is a linear combination. So given a set of vectors, a linear combination is just some weighted sum of these vectors. So if x1 through xk are our vectors, and we have scalars alpha 1 through alpha k, then alpha 1 times x1 plus all the way through alpha k xk, this is a linear combination. And these alpha 1s through alpha k's are weights. So if alpha 1 is really big, then x1 has a lot of weight. And so the linear combination is going to be nearer to x1. And this is like the most general type of combination, but we can impose restrictions on this combination. So we can impose restrictions on the set that the scalars come from. And then two, we can impose a constraint on what the, sorry, let me be consistent here. So the set that the weights come from. And then we can also impose a restriction of what the weights sum to. Yeah, so when I say weighted sum, I mean exactly the same thing as a linear combination. So the weights here are these scalars, alpha 1 through alpha k. And then, well, of course, we're summing things, so it's a weighted sum. Sorry, yeah, new terminology. So here are like the main types of linear combinations. So in the most general case, we have a linear combination, and the weights come from the real numbers, and then they're allowed to sum to anything. And if we have a set of points and we take all of their possible linear combinations, we get a vector subspace. And this is what we're really familiar with, which is like lines going through the origin, planes going through the origin, and hyperplanes and so on. Now what we're interested in today is affine combinations. So with affine combinations, our weights are still allowed to come from anywhere in the real numbers, but what we're imposing is that they sum to 1. And this gives us an affine subspace. And then there's some other combinations that you can do. It's like a conic combination is your weights must be non-negative and they can sum to anything. And this gives you a convex cone. And then if you've ever heard of like a convex hull, well, this is a linear combination where, again, your weights are non-negative, but now they must sum to 1. And so call this a convex set, convex hull, same thing. So like, I'll show you some pictures of what these look like. So I've written almost the same information as the last slide. So here's the combination, and the restriction is that the weights come from the real numbers and they can sum to anything. And so if these are our two vectors, all of the possible linear combinations gives us all of R2. But now if we impose this affine constraint, where instead the scalars must sum to 1, then what we get is the line going through these 2 points. And then if we want to do a conic combination, this will give us, well, so we're only taking non-negative weights of our vectors. So certainly we're not going to get anything like over here. So we must get something like in this direction or in this direction. And so the conic combination, or the, well, yeah, the conic hull, I guess, what do I call it? The convex cone is all of the points between these two vectors here. So that's where you get a cone from. And then lastly, the convex hull or the convex set is just going to be the line through these points, but now like these points out here aren't included, so it's just the points between them. All right, I'm going to now show you some more examples of these things. Okay. Let's see. So let's start with a linear subspace. So we have this one point here, and the span of this point is just the line here. So this is all scalar multiples of just one vector, so it gives you a line. And if we add a second vector, well, now they span a plane. And if we add another one, now we get all of R3. And so that's what this box is trying to indicate, is that the span of these three vectors is all of R3. So this one should be pretty familiar. Okay, now let's look at an affine subspace. So what you'll see right away is that what I'm indicating in red is the subspace. And so the subspace is just one point. There's actually there's a point in there. So the subspace is just the one point. And now if I add a second point, we get a line between them. And importantly, this line does not go through the origin. So this line, this is all of the affine combinations of these 2 points. And then I can add a third point, and now we get a plane. And again, this plane does not go through the origin. And if I add a fourth point, well, now we again get all of R3. Okay, the question is, I find it interesting how you need 3 points to represent an affine plane. So one basically acts as the origin. Like in what way do you mean it acts as the origin? Oh, okay, so like my point in asking is this is it's like strictly speaking, no, like none of them are the origin. Okay, so since the plane does not go through the origin, the third point acts as a reference point for the plane. Uh, sure. Yeah, I guess that's valid. I mean, certainly like when I made my plane visual, what I did is I had to like place my plane somewhere, and so it's like centered at one of these points, and then the normal of the plane is like the cross product of the displacement vectors. So yeah, I guess that's a fair assessment. So that was linear subspaces and affine subspaces. Now we can look at uh, convex cone, and my visuals here have quickly degraded. There's surely like a good way to show this, but to make this quickly, I went for a more like, I don't know, Monte Carlo approach. So the convex cone that is generated by these 2 points is uh, all of these red points between them. And I can add another one. So now there's like a cone volume. And then lastly, we'll get to convex sets. Except Studio just froze. Okay. So now the convex set of these 2 points is just the line between them. I can add a third point. And I can keep going. So now the convex set is like this tetrahedron between them. Okay. Hopefully that was a bit interesting. Okay. So here is usually the part where we would write some code. Usually we look at some math, then we look at some pictures, and then we write some code. And then, as I said at the beginning, this week I struggled to come up with things that we could code to reinforce our learning. And the reason is because we've kind of already done everything we need to do. Uh, like anything we want to do with affine subspaces, we can kind of just use what we've done for linear subspaces with some slight modifications. So for example, if we wanted to compute an affine hull, uh, how did we compute a basis for the span of a set of vectors? So meaning, I have 2 vectors, one here, one here, and their span is going to be this plane. How did we compute a basis for this span? Maybe this is, okay, let me add a third vector. So all three of these vectors span the plane, but we certainly don't need three vectors to describe it. And I guess I'll give you a hint that it looks something like this. The orthogonality is important. Okay, so the answer is that we use Gram-Schmidt. So if we have a set of vectors, like these three here, we want to compute some minimal spanning set of vectors that are also, well, right, some minimal spanning set of vectors, we can use Gram-Schmidt. And what we liked about Gram-Schmidt is that the vectors it gave are orthonormal, so they're unit length and perpendicular. So this is one way that we can compute a basis for the span of a set of vectors. And actually, we even picked up a new tool along the way. You can actually do row reduction as well. So we could row reduce the, let's see, how do I want to say this? Put the points in a matrix, put the points in the rows of a matrix. And row reduce. And so this is just another way that we can compute a basis for a linear subspace. But if we wanted to compute a basis for an affine subspace, well, an affine subspace is just like a shifted linear subspace. So to compute an affine hull, all we do is, well, first we just shift to the origin. And then we do what we already knew how to do. Then we can apply Gram-Schmidt or row reduction. And this gives us our affine hull. So there's nothing like terribly interesting to code here. Okay, are there any questions about that? Yeah. I realize that I'm not being careful about my terminology. So like span, let's see, span, hull, yeah, probably just these two. So these mean the same thing. And like for some reason, we use the terms linear span, but we say affine hull, and we say convex hull, and we say conic hull. But for some reason, for linear, we say span. And so these hulls and these spans, these are what I was just showing you. So the affine hull of 2 points was like the line through them. The convex hull is like this space in between these points. The conic hull was this, and then the linear span, right, if we have a line, it's like all of the scalar multiples of the line. So what I mean, like compute an affine hull, I mean, like we have this set of points, and we want sort of like the plane going through them. How do we compute that plane is the question. Or in general, like how do we compute the hyperplane, the affine hyperplane of a set of points. And so like the upshot was, well, we do this, the thing that we already know how to do is we know how to do Gram-Schmidt. on a linear subspace. So we just shift our affine subspace to the origin and then do Gram-Schmidt. Okay, so not exactly. Let's say this is our R3 and we have this set of points out here. And so our affine space is the plane going through them. But what we want to do is we want to shift the entire plane. Oop, that's the wrong tool. We want to shift the entire plane to the origin. And so to do this, we'll do what you suggested earlier, which is like treat one of them as the origin, and then subtract this point away from all of them. So if I shift this, so now I'm shifting this point to the origin. And then I also subtracted that same point from the other ones. And now our plane is a linear subspace. So to answer your question, you subtract one point from all of the rest of the points. Yeah. Okay. That's all I have prepared for today. I think the point of today was to just like become a little bit more familiar with the the space that we're working with. And then next week we're going to talk about uh, transformations between affine spaces. And that's really what's going to be interesting because a C-frame is a transformation between affine spaces. All right, so I think I'll cut the recording here.